This video is about using the standard normal distribution. So just a brief reminder that the standard normal distribution is a special case of the normal distribution. It's the normal distribution with mean 0, standard deviation 1, right? Often denoted by z. And this is an example of a CDF value for the standard normal distribution. It's, remember, just a left tail area. We have a z-table that allows us to look up values of the standard normal CDF. So I showed previously this example. If we wanted this type of probability, we would look at the row and column headers here, kind of add those up to get your z value or z score here. And then the interior value in the table is showing you that cumulative or left tail probability, that blue area right here. So let's just do some examples to make sure you have this skill down, because it's something that you definitely want to be able to do in sort of a quick, fluid way. All right, we'll start with one that is a CDF value itself. This probability right here, it's illustrated by the gray area in that curve at the top left. All right, so this probability is something that we can read directly off of our z-table. We go to the row that's headed 1.2, the column headed 0.05, and we find that interior value, 0.8944. All right, great. That's our answer to the first one. Okay, the second one. What's the right tail probability to the right of 1.25? This gray area right here. So let's just use the complement rule. Total area under the curve has to be 1. And so to find a right tail probability, you can do 1 minus the left tail probability, which is just the CDF value. We already found that CDF value. So just do 1 minus that, a little over 10%, 0.1056. Okay. What is the probability z is less than or equal to negative 1.25? That's our third question here. Hopefully you can see where this is going. So here we want, just this left tail probability right here. Well, it turns out that if you looked up, I don't have it on the slide here, but if you looked up the negative z values page of the z-table, and you looked at the appropriate row and column headers and looked at the interior value, you would find 0.1056. Okay, and that is exactly the same as right here. And it has to be, because the normal distribution is symmetric around its mean. The standard normal is symmetric around 0. So this probability, they have to be equal. Okay. All right. Last one. What is the probability that the absolute value of a standard normal exceeds 1.25? So let's think about this. That inequality could be true because z is large positive here in that last plot at the bottom of the slide, or because z is large negative beyond minus 1.25. Now, by symmetry around 0, we know that those two tail probabilities, as they're sometimes called, must be equivalent. So the easiest way to approach this is to find one of them and double it. Doesn't matter which tail probability you find, but in practice, remember the CDF is defined based on left tail probabilities. So if you didn't know any of the stuff up here and you just were put straight into this question, what I would do is probably think, okay, it's sufficient to find the left tail probability and double it. So I'm going to go to my z-table. I'll look at the negative 1.25 z-score. I'll read off the probability, and I'll multiply it by 2. Get a little over 21%. All right, so that's how to use the z-table. Now, In theory, I should have said before we left that slide, this type of thing shows up a lot. This type of thinking, this two-tailed probability thinking, shows up a lot when we think about confidence intervals and hypothesis tests. So that's what I'm thinking of by putting that example in there. All right, another thing that we often use is the idea of percentiles of the normal and standard normal distributions, okay? So a question here would be something like, for what z-score would the right tail probability be exactly 5%? The z-table can be used to approximate these values. You would hunt through the table to look at what's sort of closest to, in this case, if you want a right tail probability of 5%, you would look through there and figure out how close you can get to 0.95 in the interior of the table, okay? But the z-table is not really built for this purpose, so it's not going to give you a really precise value of those percentiles. It turns out that 2-3 digits after the decimal, the right z-score is 1.645. So if you had that position on the horizontal axis, then there would be 5% probability to the right, and therefore, if you looked at minus 1.645, there'd be 5% probability to the left, okay? And again, this sort of thinking is really useful when we want to think about maybe like a 90% confidence interval, where we would sort of derive that based on thinking about putting 90% of the probability in the center of the distribution, okay? 5% in each tail. All right, last slide for now is, why are we doing all this about the standard normal distribution? It's because we're going to use the standard normal to look up probabilities that we can then translate into probabilities for any normal distribution with any mean and any positive standard deviation. Okay, so let's let x be an arbitrary normal distribution here. We can what's called standardize x to create a standard normal by subtracting off the mean of x and dividing by the standard deviation of x, right? This process is called standardization. And if x is normally distributed, then z, defined in this way, will be standard normal. And this is really useful. It means we can kind of go back and forth between any normal distribution and the standard normal distribution, okay? On the graph at the bottom here, this is the x distribution. So it's a normal distribution, but not standard normal. So it might have mean, 200 and standard deviation 5, okay? And this is a standard normal distribution. And it turns out, you can see here, the gray area here and the gray area here, those things are equivalent, okay? So these are both left tail probabilities. You want to think about a CDF value of x. So that's the gray area on the left. That's just the probability x is less than or equal to whatever that value is. It might be 207 or something like that. All right. What you can do is take the z-score associated with x. You're basically saying how many standard deviations is that x value above or below the mean for the x distribution. So you would take x, like 207. Hopefully I'm keeping my numbers straight as I'm just sort of making things up off the top of my head. Subtract off the mean, 200. Divide by the standard deviation. I think I said 5 earlier. You get 7/5. Okay, so that's your z-score, right? 1.4 in this case, right? 207 is 1.4 standard deviations above the mean of the x distribution. All right. Now that's equal to the cumulative probability for the standard normal at that z-score, right? Which is a number that we can just look up on the z-table. So that's what this is showing. This is the standard normal distribution, mean 0, standard deviation 1. This is our z-score, 1.4 in this case. And if we look that up on the z-table and find a probability, easy to do, 1.40 right here, so about 92%, okay? Then what we're saying is, for any normal distribution, 92% of the probability lies to the left of 1.4 standard deviations above the mean. Okay. If 207 is 1.4 standard deviations above the mean of the x distribution, then 92% of the probability will lie to the left of that. Right. So that's how we use the standard normal to find probabilities associated with any normal distribution.